Many thanks to Manisha for inviting me to this. I mean, she's really been one of the most energetic people around and has motivated us to speak up at these kind of public events. And a lot of thanks to the Google developer group community in Kolkata, which has been so active. So we've heard a lot of really good talks since the morning, very energetic ones, etc. And many thanks to Yash, who just came before me, who pretty much set the stage. Thank you. And I think I'm waiting for my presentation to come up. It's going to be a bit dry, a bit technical, and probably more for beginners. I hope it interests some of you. I don't know. I need the clicker.
Okay. Ladies and gentlemen, I would request you to all be seated and avoid any form of chaos right now. We have a session going on. Thank you. Over to you, Miss.
So I'm going to dive right in, and I'm going to start with why we need word vectors or word representation. So we generate a lot of text online these days, and that text needs to be computationally understood. But before we understand what it means to have text computationally understood, there's been a lot of study in linguistics on understanding what we try to mean when we say a few words or when we write a few words. What exactly are we trying to say? So linguistics has been a long study on that. And from there, people have tried to understand computational linguistics. Why? Because you cannot understand, you cannot have a person read everything everybody is posting online and then, finding out what somebody is posting and what somebody is not posting. So you need a computational way to do that. And usually to begin with, you came up with these ideas that, okay, language has a certain grammatical rules. So you find from the study of linguistics what are the grammatical rules and what else, and how does the sentence get structured, and probably try to map that to some computational rules as well. But that was difficult when you have so much data online, and what people post online and what people write even on websites of their own is not really adhering to what that language's grammar that is studied by linguistics can have. So there was a shift. And there was a shift when we started to try to think about text from the word usage. So words, if you just consider the words that are used and in some way try to understand the meaning of what a person has written from just what words they have used. So the thing is, the first thing that comes to people's mind is find out what are similar words. So the entire thing about word representation and understanding meaning of words in text comes from the simple idea of understanding which words go with which other words and which word means other words. So it's difficult to understand that challenge, but let me try. So if you had two statements or two words, let's say like hat and cat, they're different in only one letter, but their meanings are very different. You would find them in very different sentences. I wore a hat. My cat is sleeping. So these are different words. Now, different sentences, but they differ in only one alphabet, let's say. So just taking the alphabet level representation of those words do not actually convey that much meaning to its word. So there was a interesting. So I have referenced whatever I have, because most of this material you'll find online. I've just bunched together a lot of online material together to make up this talk, so you'll have all the references, you can go back to them. So Firth is somebody who said that a word is characterized by the company it keeps. What it means is words that occur together probably have a similar sense or a similar meaning. And that comes from a concept of distribution semantics. And when you mean semantics is what is the meaning. So let me go further. Oh, not this one. Okay, my slides are not in focus. Okay, so, well, I don't know what's wrong, but let's say I take two sentences. So I'm going to start with what was usually the way that people started with representing words as vectors. So let's take two sentences. Earth is the third planet from the sun and Jupiter is the largest planet. So these have certain words. Earth is the third planet from sun, largest Jupiter. Now what you can do is, let's say so these sentences are also considered, you can consider them as documents. They can be one sentence, they can be many sentences, that's a document. And these words would be considered as terms. So each of these terms will have some number of times that it has occurred in each document or each sentence. So just considering that, you would come up with something like a term document matrix, where each term has the number of times it has occurred in each document, which is a combination of sentences. Now, so you can consider that line, that term one, which is one word, that entire thing is one representation of that word. It's a numerical representation of that word. So now what you can do is you can try to various similarity measures, because once it is in numbers, in a form of numbers, you can add, subtract, multiply, divide, whatever, vectorically.
What do you mean by terms?
Terms are words. So earth would be one term, right? So what it's difficult to show without that diagram is that a lot of these are going to be zeros. Even if you have large number of documents, most of these things are going to be zeros, because most words are not going to be there in each document. So okay. This might be a mistake. This is just, yeah, log 2 by 1 is definitely not 0. So this is a mistake. But so basically, since they were all zeros, so the TF-IDF is not, TF-IDF is the next way of doing the word vectors. But why were we doing TF-IDF, not just the term weights, is because, not because of the zeros, but because in term weighting, you'll have a lot of these top words that Yash was talking about, like is the, which he considered is important. In most NLP tasks, those are not considered important. They give a lot of errors when you're trying to understand the meaning of a text. So in that case, you want to get rid of the frequent words, and these frequent words may not be always is, the, etc. in a set of documents, because let's say you have a set of documents which are just pertaining to the enterprise of Google inside. So Google would be a really kind of a stop word. You want to get rid of Google from your analysis there. So that you can do by normalizing it against the number of times it occurs in various documents. That's the inverse document frequency. Sorry? Yeah? Yes. Yeah. Semantics, because this is just the number of times the term occurs across the document. no, this is the entire document. So there's one document, there's another document, there's another document. Yes, I mean, it's not entirely true that it does not capture any sense. It does capture some sense, but it doesn't capture it that well. So this is the formula for TF-IDF, so this is the number of the term frequency comes from the term document matrix that I showed before, the number of times a word occurs in a document. And it is normalized by the inverse of the document, the number of times it occurs in a document. Across documents. Now what happened in that is also that you'll find a lot of zeros. Even after normalizing, mostly those terms are not present in a lot of documents and so on. So there's a lot of zeros there. So you want to have a more compact representation. So to have a more compact representation, you use this comes from linear algebra. I am not going to go into this. It's derived mainly from the whole concept of eigenvalues and eigenvectors, which you must have studied in linear algebra. It's for a more general matrix, not just for a square matrix. And when you do that, let's say this is your term document matrix. Documents means a set of sentences, and terms are your words. And as you see, these are, presence of those words here. And when you run your linear algebra decomposition, the SVD decomposition on it, you come up with these kind of a reduced set, which is, as you can see, the bottom, you won't see a lot of zeros here. So these are more compact representations of the same terms, and so this is one of the older forms of understanding what word representation or word vectors. Now, and these have been very useful. In fact, when you want to compare and see how a query or a query, a natural language query that you put on Google matches your web documents, you can use these kind of things, and it'll give you some kind of a similarity score. You use cosine. So so then what happened is those things did capture some meaning, but not as well. They had they're not able to understand between the context. Like, yes, people used to do some kind of WordNet meaning repositories to understand the meaning of words, etc. But to understand from the distributional semantics point of view, that one word, the representation of one word, is not just the term frequency or the frequency of its existing in a document, but it depends on the words that are beside it. So when you represent that word, or you try to calculate the vector representation of that word, you actually have to consider the vector representation of words around it. So that's what Word2Vec did, and Glove and so on, that Yash was talking about, is that it took the input, the one-hot encoding input of word. Okay, so this works. So Word2Vec works well if you train it over a really large corpus, a really large corpus. So the one that Yash was talking about, the Glove corpus, is run over, let's say, the whole of Wikipedia or the whole of Google News. So that's millions and millions and millions of documents. And so there's a large vocabulary of words. There's like millions of words itself. And those words, when they occur with each other, those in this neural network, they when you input those words, the encoding of words, they will, this one-hot encoding will get updated with the learning weight of words which occur along with that word. So you won't have a just a term frequency in the word representation. You'll have the weight of that term and terms surrounding it that are found in the documents, influencing the values in that word vector, in that representation, when it's finally trained. So right. So these are certain ways, and so it might seem that this may not be so, it might seem this is just so mathematical. Does it have any relation to semantic meaning, etc.? But it does. I mean, if you plot so these are multi-dimensional vectors, and if you plot them, you'll find that that the words with similar meanings are actually close to each other. So, for example, you can see that things which are found together in documents are actually closer to each other, and they're fairly separated from words which are farther away from each other. So this helps you understand meaning of documents and understand. Yeah. Okay, I'm going to go. So so since I was kind of focusing on using word vectors, I just wanted to show of hands how many of you are familiar with Python. Oh, great. So everybody's familiar with Python. And how would you are familiar with Keras, Pandas, SciPy? Oh, quite a few. So then I think this will be very beginner stuff. So what I'm trying to do is I've taken up a Kaggle task. It's a multi-class classification task, text classification task for MBTI personalities. This is a data set, a very well-known data set on Kaggle. And it has 16 MBTI classes, personality classes. And this blog, I've referenced it, has quite a good explanation of how to go through and explore the data set. I would recommend. So as you can see that each of those classes has quite a number of words, etc. So yeah, let me go through this. Yeah, wait. Is this it? No. Okay. So I'm going to just go line by line simply. As a very beginner, I'm sure this will seem very simple to you, as to how easy it is to use pre-trained word vectors. So there, you can download these glove word vectors, and I've chosen the 300 dimensional one. There's 100 dimensional ones. So basically, what it means by 300 dimensional is there's 300 integers, floats that so it's larger context, so to say. So you input you take in the glove vector embedding file is just one word, that is the vocabulary word, and its word representation. And so you can easily read it into an array. Next, you obviously are going to okay. Sorry. Yeah. Next, you're just gonna just find out what is the. What did I do? Just flatten out the embeddings so that they are features. You really don't need to do this. I just did it for just to show you that it can be done. And you can put in other features which are not required, because usually when you use embeddings, you can just use an embedding layer in Keras. But here you can also, just for demonstration, you can have other features like words per comment, how many links there in each comment, because these are tweets and tweet comments.
So are you creating these features also like question per comment?
Yeah. In this, but you usually don't need to do that, because if you go to the link that that I've referenced, when you have embeddings, you don't need to add any extra features. Just the embedding layer itself would do. But I've just done this to show you. So it's pretty simple, as you can see. You just transform your labels to categorical labels, and split your training and test set, and then you start a sequential model. I think that's kind of like an RNN or something, and then you add one layer, and then you have a softmax layer, because there are 16 classes. There's a multi-class classification. And then, of course, you fit and you train and you predict. Obviously, it doesn't do well, because you are supposed to have an embeddings layer, not a thing layer. You could even run a simple random forest on it. Doesn't give great accuracy either. A multi-class classification is tough.
What was that 40 by 307 you had in the main?
Which one?
See,
Input dimension. So there are 300 embedding vectars, and yeah. Well, so this is the. This is where you can get the this link also I have added. So this is where you get the better way of using pre-trained embeddings, where you can I don't know if you can see this. You can actually use an embedding layer, which is much simpler. So I'd recommend that you go over what people have done and try it out on your own. No, it will give good results. It's just that I didn't run it really. I mean, I added more features, and so you don't really need to do that. You have to create your, architect your thing well. Yeah. So Word2Vec really worked well, but and it has, as you can see, it is definitely something that you should go to if you want to. And it's like the pre-trained word models are in text format, so it's really easy to understand what is going on. I'm sorry I didn't make it much easier, but yeah. But what is new? What is new is what has come out from Google. Is the XLNet. So I think Yash touched on the idea of using attention or multi-head attention. So what happened with Word2Vec was that even though the words that are within the same document had an effect on the word representation, it was not that context sensitive. In the sense that it was not bidirectional. You're not looking at the sentence from both, going from front to back and back to front. And that makes a lot of difference when it comes to understanding the meaning, as people have found out in other models as well. So, and also Word2Vec, when you train it on a smaller corpus, it doesn't really help you get a lot of meaning out of that. So ExcelNet has come out, which has very long range dependence, that is even 50,000 words apart. If the words are there, their meanings would still be captured together. And the pre-trained model that ExcelNet has can be fine-tuned for every task that you want to do and give much better accuracy. It's bidirectional, that's the main point. And it is based upon Google's model of Transformer XL, which is basically, forget about the RNN, as Yash was talking about in his hierarchical attention network or hierarchical architecture networks. You remove the whole RNN, and it's just a layer and layer and layer of attention network. And this is, since this is very new, I wouldn't be able to go into very technical details about this, but yeah. No, this has nothing to do with the knowledge graph. I think you've asked this question before. Knowledge graphs have, knowledge graphs is a completely, Right. No. Knowledge graphs is completely different. Knowledge graphs is, I can take this offline with you. Yeah, I'll take this offline. So here we are just trying to understand the meaning of the words that are in the sentence. A knowledge graph would try to incorporate meaning across whole spaces of knowledge. No, this has nothing to do with an ontology. This is just from whatever text you are giving it. So you might have a question answering task. You might have a text classification task. You have data which is not that great, which is poor, which is half, a lot of this. So this will try to understand what is the meaning from whatever documents you've given. Yeah. But my point, why I brought this up is that XLNet is also not that difficult to use. When you're trying to use XLNet, it's not that difficult to use. As you can see, you go to the You go to the GitHub link, download the ExcelNet, and instead of these flat files, glove vectors was a flat file with one word and then the whole representation of that word, the vector, the floats. In this case, it's just a Keras checkpoint, a model checkpoint. So you can actually take up that checkpoint. Let me go. So the README is pretty good of the ExcelNet if you want to really start off on some tasks yourself, and these would give much better results. You'd be surprised by the kind of results you get. And yeah, so let's take the earlier multi-class text classification task that we did, and let's say you want to run it using ExcelNet. You can just download the ExcelNet model, which has the model checkpoint, and you can just go ahead and go to that run classifier.py and just this data processor. So these are already there for certain data sets. Okay, you just have to tweak some of them so that it matches what your data. So here these are like the train examples and the dev examples. If you have the labels, so you just have to probably transform your labels. That's it, and you can. So these are. It's pretty simple if you want to modify this run underscore classifier.py file to just create your own classifier using existing ExcelNet and probably fine tune it as well. So that's all I had. Yes, it is the pre-trained models that are there. These are compiled checkpoints. So whatever ExcelNet's code base has, I'm happy to say it's not that difficult to use, even though it has come up really recently, like last month, and Yes. The word representation is captured as a final checkpoint model. So it'll when you incorporate it in your pipeline, you will put it as an embedding layer. Okay, that's all I had. Yes, questions. Right. So glove vectors. Okay, it's too far ahead. But the only difference is that BERT does not, BERT masks. So so basically the links that I have shared will give you a very good idea of why ExcelNet is better than BERT. But the main point is that BERT masks the word that it's trying to predict, and therefore it loses some meaning, and also it does its range of context is smaller, because BERT is based on transformer architecture, whereas ExcelNet is based on the transformer XL architecture, which has a bigger context. And the more the context is, the more you can get long-range dependence on the words. Meaning of words is dependent on the company it keeps, and the company it keeps, that is the context, can be far apart or maybe close. So that's the difference between BERT and ExcelNet. It does. I mean, the paper that they have shown, and you can run these examples. It's actually, because of this run classifier.py and other ones, you can actually download quite a few of their data sets and benchmarks, and you can run them yourself and see that ExcelNet actually runs way better than BERT. But that's okay, I guess. BERT also does really well. So the big difference coming from Word2Vec to these models, BERT and ExcelNet, is that BERT and ExcelNet, you can fine tune the models and then get a better accuracy. And Word2Vec, not very easy to just fine tune. You have to use what is pre-trained from like Yash said, on a big data sets. That's like all of Google News, so that you have all the words that are there in the world already having their own vectors trained. So I'm sorry I kind of rushed into it. Any more questions? Yeah. Yeah, so Word2Vec is great. It's not bad. In fact, the TF-IDF thing that I showed you was actually used. I mean, the SVD, the LSI is actually used. And if you can try it out, it's much simpler to try out. And you can see that all of these actually have good to work out well. But it's like, how accurate are they? What is the final accuracy that you're getting? So yeah, I mean, Word2Vec works well. You want to start with Word2Vec, start with Word2Vec. I feel that it's more easier to do than these XLNets and stuff. Yeah. You apply it in various text NLP tasks, like for text classification, wherever you need the meaning of the language that is there or the text that you are using. There you would use Word2Vec. For example, text classification, yes, text clustering, and various other textual tasks. For example, I mean, yeah, all of these, I think Yash showed us a very interesting example. So there are many places where you'll need NLP and you'll be using these word vectors. So RNN is what you use to do the classification task itself. But how do you compare between words? You cannot compare between words by the alphabet. That will not give you much. Hat and cat differ only in one alphabet, but just finding out the distance between hat and cat as being one because they differ in just one alphabet is not going to give you much. These word representation allow you to find distances and similarities between them, and that too computationally. So I hope. Yeah, I'm done. And nobody else? Yeah, okay.